Okay. Okay, so in the last plenary seminar of Encontro Nacional of SPM, we are very happy to have Hugo Dominil Copin. He is a leading expert in the area of probability and mathematical statistical physics. After completing his PhD in 2011, under the supervision of Stanislav Smirnov, Hugo was a postdoc and assistant professor at Geneva University, and since 2016 is professor at the IHES. So Hugo has received many prizes. I will mention only a few. So in 2015, Cours Picot of Collège de France. 2016, the prize of the European Mathematical Society. 2017, Ising's Prize and Loeb Prize, and 2019, the Dubrovshin Prize. From the address of the Loeb Prize, I mentioned here, Hugo Dominil Copin is best known for his results, for his work on phase transitions in two-dimensional lattice models. He and co-authors proved a wide range of long-standing art conjectures. More recently, in fact, just this month, he co-authored a paper with Michael Ising in the Annals of Mathematics, so July 2021. And this is a paper on marginal triviality of the scaling limits of critical four-dimensionalizing models and 544 models. So this is a problem that has resisted for several decades and is in fact of central importance for the standard model of particle physics, the triviality or non-triviality of 5-4 scalar field theory in 4 dimensions. Today, Hugo will tell us about the emergent symmetries in planar statistical physics. And without further ado, I leave you with Hugo, please. Hugo.
Well, thank you very much. Should I start right away?
Yes, please.
Okay, very good. So thank you very much for the invitation. It's a pleasure to be giving this talk, even though it would have been even nicer to be in person at the meeting. So what I wanted to do in this talk, I'm not sure people see my slides. They see? Okay, very good. Perfect. So what I wanted to do in this talk is tell you about a very intriguing phenomenon in statistical physics, which is the emergence of spatial symmetries when you look at what we call the critical point. So I'm going to explain, of course, what all these terms mean, and you are going to see it's going to be pretty, let's say, clear what I mean by that. But I hope to be able to give you a hint at all these things and to present some recent results which is related to all these questions. Okay, so let's start with the beginning. What do we want to do? So we want to understand what we call continuous phase transition. And I would like first to tell you what a phase transition is. So a phase transition in a physical system, it's not necessarily a notion in math, it's a notion in physics, even more, and chemistry, even more than math. So a phase transition is a drastic change of the behavior of a system when you change its parameters continuously. Imagine you change the temperature or you change the pressure, you change the parameter continuously and it completely changes at some point, completely change the system. So maybe the most famous phase transition you encountered in your everyday life is for water, where when you cool down water, you end up with ice exactly at 0 degrees. And if you heat it, you end up with vapor exactly at 100 degrees. So it's a change, drastic change of the behavior of the system, exactly when you vary continuously the temperature in this case. In fact, you could also vary the pressure. It's a little bit more delicate, but you can vary the pressure and also change what is happening. But this is just one example of a phase transition. There are many more. And in particular, there is just to mention another one, the phase transition in magnets. So you take a magnet and you heat it at a certain temperature, which is called Curie's temperature. It was invented by Pierre Curie. At the Curie temperature, the magnet ceases to be a magnet. It doesn't point north anymore, if you want. So this temperature is yet another example of a place where a phase transition occurs. You have many other phase transition, in particular in porosity of a medium. If you start digging into something, there is a point where it starts to, the water or any fluid start to go through the medium. This is another type of phase transition. It's actually the one that we will study in a minute. Just for people who know a little bit about this thing, I want to be clear that we are going to actually focus on one type of phase transition, which are called continuous ones. So sometimes phase transitions are discontinuous, something very drastic happens. Sometimes they are continuous. I don't want to enter into a mathematical definition of this, but we are going to focus on continuous ones. So don't shoot at me if you hear things that seems not relevant for all phase transition. It's because I will always have in mind this continuous phase transition. And the goal is going to be what? Well, the goal is going to be to understand how the system evolves when you vary the parameters through its phase transition. For instance, if you vary the temperature through the phase transition of the exactly at Curie's temperature, how does a magnet evolve? How does it lose its magnetization, for instance? Okay. So there are millions of, infinitely probably even many different types of phase transition. So I'm not going to start reviewing all of them. I'm going to focus on one specific example, which I think is a good one to highlight what I want to be describing to you. So I'm going to focus on porosity of a medium. And the story behind the thing is, can we understand how a fluid goes through a porous stone? So there was a paper in the 50s by Broadbent and Hammersley. It's the first paper in the area that proposed a model for this system. So what they propose, and that's what is written in the abstract, is to model the medium, not the fluid, but the medium. So for people who do PDEs and are used to fluid theory, we are going to take a completely different point of view. We are going to focus on the stone, if you want. And what they propose is to imagine that the stone is some kind of random maze. Okay? In the stone, there are atoms which are either connected by tubes which water can flow through, or by tubes which are dammed, which are not letting water go through. And the idea is going to be to understand how water is going through this when you pump water in, say, at some place. So they call it a source. You pump water and you try to see where it goes. Okay? So this is just a description of a vague description of what they do in this article. I'm going to be more precise in a second, but just to say that the story was a little bit less fun than it may look like. Maybe it doesn't sound fun at all when I describe it, but it can look fun to look at water going through something. But in their original paper, they actually had in mind gas going through mask as a weapon. So this is sometimes you don't have sometimes it's not the best attention, but it led to a very, very good model. So more concretely and more mathematically, what is a percolation model? One way of looking at it is the following, is to imagine that your stone is a graph. So it's a graph G. It has vertex set V and edges E. And I'm going to think of my stone as a random subgraph of this kind of base graph. I want to be modeling whether, if you want, the bones, the edges between vertices are dammed or not. So I'm going to take a subgraph omega. It's going to have exactly the same vertices as the original graph, but the set of edges is going to be a subset of the set of the original edges. So the set of edges are going to be the edges through which water can flow. And it's not the case of all edges. So of course, when I tell you I'm going to take a random subgraph, well, there are many ways of picking something at random, so I need to tell you exactly what I do. And maybe the simplest example, so here I just depicted my original graph and the graph omega in red. So a typical example of a way of sampling at random is going to be to pick every edge of the original graph. You are going to toss a coin. If it's face, you put the edge in the graph. If it's tail, you don't put it. And you just imagine that your coin is biased. It falls on face with probability 1 p and tail with probability 1 minus p. Okay, so for every edge, you choose at random whether it is in your graph or not, and you do this independently for every edge. It's called Bernoulli percolation, and it's probably the most famous example of a percolation model. Okay, so it's a talk, so I want that you see nice pictures. So let me show you 3 simulations. So it's somebody like simulated what is happening, and he did it for 3. I think it's actually due to Raphael Cerf, these simulations. And he did it for 3 different values of P. In the middle, for instance, this is exactly what happens when you take a fair coin. For every edge, you toss a fair coin. So you will keep the edge with probability half, and you will remove the edge or forget about the edge with probability half. And what you see here is just a coloring of the different connected components in my graph. The connected component is going to be an equivalence relation for the property to be connected, that 2 vertices can be linked in the graph. Okay, so just the picture here is depicting this is 1 connected component in purple, 1 connected component in green, etc., and this is what happens at 0.5. Now, this is what happened when you take a biased coin, which is biased towards tail. So you keep more than 0.5 guys. You keep P, proportion P, which is larger. Then what you see is a picture which is completely different from the picture of the fair coins, because here you see that there is a huge connected component, which is almost everywhere. It's a C that is almost everywhere, and some small islands, some small connected components inside it. On contrary, when you take P smaller than 0.5, then you see that the connected components have a tendency to be small. It's not that clear on the picture. I should maybe have taken an even smaller P, but the picture here is different from this one because the connected components are smaller. So it seems that at 0.5, something drastic happens where you go from a place where you don't have so many connected components to a place where you have so many big connected components to a place where you have a huge one, like a huge connected component everywhere. So this is just an introduction to percolation with the example of Bernoulli percolation. But before I proceed forward, because it's going to be important for what happens next, let me highlight one thing. I said that there are many ways of picking a subgraph at random. And I want to insist that Bernoulli percolation is just one way. There are many other ways. And actually, many of these other ways are very interesting models as well. So for instance, just to make one example, which is going to come back later, you can consider what we call FK percolation for Fortune and Castellan. And this percolation is defined as follows. So here, I look at the probability of omega, which is proportional to P to the number of edges in omega, 1 minus P to the number of edges which are not in omega. If I stop here, it's an easy exercise, in particular for people not in probability, to check that this is exactly the probability of a configuration in Bernoulli percolation. But what I'm going to add is an additional term, Q to the number of connected components, where Q is a positive number. So you see, when Q is equal to 1, it's Bernoulli percolation, but as soon as Q is not equal to 1, I'm kind of twisting the measure by rewarding, if Q is larger than 1, say, by rewarding connected connected component, cluster with many connected components. Graph with many connected components. So some people may be dying from a heart attack right now because they are thinking, oh, but this is not a probability measure. And you are entirely right. If I want a probability measure, I need a mass 1. So I'm going to add a renormalization, which is called the partition function, just to make it a probability. Okay, that's one example of percolation model. Let me describe some others which are very nice and that people like, because they make very nice drawing and they are also very relevant for physics. So one example, for instance, that I like is called Voronoi percolation, where you do the following. You put points at random in the plane, usually according to a Poisson point process. And what you do is that you draw the Voronoi selves of each point, meaning the set of points that are closer to the given point than the other points in my set. So it partitions the plane into cells, and then you color each cell black with probability P and white with probability 1 minus P. So the black edges, they are like the places where water can flow, and white edges are the places, white points are the places where it cannot flow. So you end up with a nice picture like that, and you can also study the connectivity properties of this random set. There are many other ways of doing. You can take a random continuous function and take the set of points where it's larger or equal to something. This is also an interesting percolation model. It leads to very nice connection to algebraic geometry, to number theory. So, this is also very nice models. I just wanted to let you know about that you have some kind of glimpse at the variety and the richness of these models. But for now, we are going to focus on FK percolation, or even if you are a little bit confused about everything I'm saying, focus on Bernoulli percolation, I'm fine with it. So we are going to take FK percolation on Z2, so on the full lattice, not just on the finite graph, but on the full square lattice. And we are going to see, or I'm telling you rather, I'm not going to prove it, that there is a phase transition in the following way. There exists a critical parameter, PC, below which there is no infinite connected component in my graph, almost surely. So with probability 1, all the connected components of omega are finite. And for P larger than PC, with probability 1, there exists an infinite connected component. So you see there is a drastic change. No infinite connected component for P smaller than PC, and an infinite connected component for P larger than PC. So there is something very delicate happening at PC that you completely change the picture from no infinite connected component to a unique, in fact, infinite connected component. If you think of water flowing through the thing, you can think of the following. Imagine you pump water at 0, and you see whether water can flow to infinity or not in my graph. Then a restatement of what I just said will be the following, that the probability that the water flows to infinity, the probability that 0 is in an infinite connected component, is 0 when P is smaller than PC, and it's strictly positive when P is larger than PC. And this value, we usually call it theta PQ, and it's kind of a measurement of the porosity of your stone, if you think of the physical system that this model is describing. So a phase transition here between 0 probability of flowing through infinity to positive probability of flowing through infinity. And once you see that, well, natural questions arise. First question is, what is PC? What is PC? Second question is, well, how does theta of PQ, the porosity, how does it evolve? And the prediction is a beautiful prediction that it should behave like that. So it's 0 below PC, and it should become like that for P larger than PC in the sense that there should be a constant alpha of Q. It's called a critical exponent, so that theta of PQ should behave like P minus PC to the alpha of Q plus little o of 1, meaning when P tends to PC, it should behave like P minus PC to the alpha of Q at first order. So this is a conjecture. It's a beautiful conjecture. It's an important conjecture because the value of this critical exponent is something which is relevant to physics as well as mathematics. And somehow everything I'm going to say afterwards lean towards proving this. I mean, overall, it's kind of the goal at long scale. Long time scale. Maybe infinite time scale, I don't know, but I hope finite. Okay, so answers first. Let's start with answers to this question that I don't want to be discussing during this talk because it's not going to be the center, but that I want to mention that at least you are not confused about what will come next. So the first answer is that one can compute the critical point. So PC is in fact equal to square root Q over 1 plus square root Q. You remember there was, in FK percolation, there was a parameter, which was Q. And as a function of Q, it behaves like square root Q over 1 plus square root Q. And in fact, when Q equal 1, for people who want to stay with Bernoulli percolation, it gives PC equal 1/2. And this was actually known since case 10 in the 80s. That's the first answer. The second answer was obtained in a series of 2 papers. And it says the following. It says, if Q is between 1 and 4, then theta PQ is behaving like P minus PC to the 1 minus, it's bounded by P minus PC to the 1 minus C. So it's a little bit like here, except it's just a bound, and it's a bound by some constant. We don't compute the critical exponent. On the contrary, when Q is larger than 4, this picture is completely wrong because in fact at PC, theta PCQ is strictly positive. So it's completely different. This is called a continuous phase and this is a discontinuous phase transition. The last item I want to tell you before I really dive into the crux of the talk is a recent result with Ioan Manolescu that says the following. I'm not going to state the result, but I'm going to mention it roughly, mention roughly its contents by saying that understanding theta of PQ is actually, can be done by only looking at what happens at the critical point, at PC. It's some deep theorem using, which is called scaling relations, and that relates what happens near the critical point to what happens exactly at the critical point. And I wanted to mention these 3 theorems in order to be justifying what I'm going to now do, which is I'm going to focus from now on Bernoulli percolation at P equal PC, so at the critical point. Okay? And the whole story and the nice part of the story I want to discuss is exactly at the critical point. So you can forget everything and think that now I have a given percolation model, Bernoulli percolation model on the square lattice. So I sample edges at random by sampling fair coins for every edge. And I'm going to focus on this thing. Okay, so what do I want to be saying on this thing? As mentioned in this theorem, understanding theta of PQ requires understanding the properties at the critical point. And more precisely, it requires understanding the large-scale properties of my system, what happens at large scales. So I'm going to do that by, instead of looking at bigger and bigger distances, I'm going to rescale the lattice. I'm going to shrink the lattice in such a way that I can still make my pictures fit in some given size. Okay? So I'm going to look at omega delta, which is percolation, not on Z2, but on delta times Z2, where delta, you think of it as a small constant. Okay, so this is a simulation of critical percolation on delta Z2. And what we want to understand is the properties of this thing. So you will agree with me that thinking of Bernoulli percolation configuration omega as a subgraph of the original graph is going to become really messy when that delta tends to 0. Because you are going to have a bigger and bigger graph, more and more complicated graph. So in order maybe to simplify our mental picture of what we are doing, I'm going to rephrase it as follows. I'm going to think of percolation not as a subgraph of omega, not as a subgraph of delta Z2, but as a collection of loops which are the boundaries of the connected components. First, it makes a nice picture. And second, it's very clear what happens when delta tends to 0. I just have a random family of loops, and I can try to understand whether it converges to a random family of loops in the continuum. So in order to speak of, so I have this family of loops, and maybe for people who want to think of this as a metric space, they would like to have a distance between family of loops. Take the most natural one you can think of, which is going to be the following. For every, you are going to say that the distance between two families of loops is small, smaller than epsilon. If whatever a loop in the first family of loops, let's call it gamma, whatever a loop of radius at least epsilon, there exists a loop in the second configuration, which is very close, which is close, let's say, at distance epsilon of the first one. And vice versa. For any loop in the second one, there is a loop in the first one that looks very much the same. Maybe I'm a little bit non-rigorous in the way I'm describing this distance, but it's not something central in the talk. So I hope I'm just giving you an idea that one can define the distance. It's actually a good exercise to try to define it if you want, to define it really properly. In fact, you need to do something slightly different, so it's a good thing. But let's assume we have a nice distance on family of loops. Okay, so what is the first conjecture? And I'm going to be mentioning a bunch of conjectures on this model. The first conjecture is that when you think of omega delta as a family of loops and you let delta tends to 0, so you have, if you want, a sequence of random objects, of random families of loops, well, the conjecture is that these random objects, they converge to an object in the limit, which we are going to call omega continuous. So if you prefer, when you look at delta smaller and smaller and smaller, the random family of loops becomes closer and closer to a continuum limit, which is going to be a random family of continuous loops. It's very unclear how this thing looks like at this stage. But the conjecture, it goes back to physicists, is that when delta tends to 0, the random object converges to something. Okay, it's a big conjecture. But once you have this conjecture, you can play a nice game, which is try to describe what is omega continuous. And in order to describe an object in physics, very often what you try to do is to describe its symmetries. Why? Because the more symmetries you have in an object, the fewer parameters you need to understand to describe it. So a very symmetric object is an object which is very simple to study. So we are going to try to see whether this omega continuous has symmetries. And the first claim is that its mere existence, just the fact that it exists, implies at least two symmetries. The first one is a symmetry by scaling, meaning that omega continuous has the same law as lambda times omega continuous for any lambda. The second one is that omega continuous is symmetric under translation, meaning that omega continuous has the same law as the translation by x of omega continuous. So how do you prove these facts? I can even really prove it because it's really not that complicated, if I may. Okay, good. So first thing, for the scaling, what you do is the following. You observe that omega of lambda delta, when you look at percolation on lambda delta, well, this has the same law as lambda times omega delta, simply because that's exactly what we do. We rescale the lattice by a factor lambda. But when you take delta to 0, you realize that omega delta and omega lambda delta both converge to omega continuous by definition. Therefore, omega continuous has the same law as lambda omega continuous. It's really almost a tautology from the definition of omega continuous. Of course, it's if omega continuous is well defined, if the limit exists. And you can play exactly the same game with translations by using the fact that if you take the lattice Z2 and you translate by an integer, by a point which is in the lattice, then the model is invariant automatically. Okay, so we get two symmetries out of the existence of omega continuous. But what I claim is that there is a third symmetry that is even more important in the model. So the third symmetry is that omega continuous is in fact symmetric under every rotation by an angle alpha. You can take whatever rotation you want from whatever angle, omega continuous is going to be symmetric under this. And this is very, I mean, at least to me, it was very surprising at first, the first time I encountered this conjecture, because it's completely clear that the model is invariant of the rotation by pi over 2 or pi, because these are symmetries of the original lattice Z2. But why on earth would it be invariant under any rotation? This is, I mean, at least to me, it's a very surprising conjecture. And this conjecture, we owe it to physicists, and they have a beautiful way of justifying it, even though it's a way which is a little bit using a hammer to kill a poor fly, which is to invoke an even stronger conjecture. And this even stronger conjecture is called the universality conjecture. And this universality conjecture says the following. It says omega continuous should be the limit of any scaling limit starting from any planar lattice. You don't need to start from Z2. You could start from triangular lattice. You could start from hexagonal lattice. When you take the mesh size of delta to 0, you should converge to the same omega continuous. And if you think, if you buy this conjecture, which seems like a very strong statement, but if you buy it, then proving rotation invariance is very simple. Because what you do is, you say, if I start from the square lattice and I take the limit, I end up with omega continuous. But I could also start from another lattice, which is just a rotated version by an angle alpha, and I take the scaling limit. If I do that, I just end up with omega continuous again. But this rotated thing also has the law of rho alpha times omega continuous. So that's how you get the rotation invariance. So you can tell me, okay, but I mean, this universality conjecture seems like an extremely strong statement. And that's true. It's probably, I mean, it's definitely much harder to prove than the original rotation invariance conjecture. The proof of that is that we actually prove rotation invariance. That's what I will be describing, but we are far away from understanding universality. But let me just, especially because I know that in Portugal and in Brazil, people love this type of mathematics. So let me mention where the conjecture comes from in the mind of physicists. It comes from a dynamical system interpretation of the rescaling. It's called the renormalization group, and the idea is the following, is that if you rescale everything by lambda, where lambda is smaller than 1, well, you can think of it as applying a map, T lambda, that would be defined on the space of models, of percolation models. But then you can think of omega continuous as the limit when n tends to infinity of iteratively applying the map T lambda. So applying T lambda to the n to the original model. So what do you get from this interpretation? well, you get a very nice observation that omega continuous should be a fixed point for T lambda. And then, well, you know, if you are ready to believe all these things, maybe you are ready to believe that this dynamical system has only one fixed point. But if it has one fixed point, whatever the lattice you start from, when you iterate the map T lambda, you end up with a fixed point of T lambda, so you end up always with the same limit. The small, like, well, or huge, let's say, elephant in the room is that we know as mathematicians and actually physicists as well, of many systems, dynamical systems, that don't have a unique fixed point. So proving the uniqueness of the fixed point is a very, very difficult task. So that's why this conjecture on mathematical grounds seems extremely difficult to prove. In fact, it's not even that simple to state it correctly. But that's the physical intuition, and I wanted to share it with you. Okay, so at this stage, if we believe omega continuous exists, and if we believe physicists, which we should often do, maybe always, then that means that this omega continuous is scale invariant, translation invariant, and rotation invariant. 3 symmetries. Well, I claim that there is a symmetry to rule them all. There is a symmetry which is stronger than all these symmetries and which is hidden in the model, which is called the conformal symmetry. So what does it mean to be conformally invariant? It means the following. It means that if I look at omega continuous in a domain, f of omega, where f is a conformal map from omega to f of omega, then omega continuous in this domain has the same law as the image by f of omega continuous restricted to the original domain omega. A picture is going to help here, because this is always a little bit confusing. Imagine you have a domain omega, and you have a conformal map to another domain f of omega. Then I claim that here I can define 2 families of loops. I can first take the square lattice here and take the limit when delta tends to 0 of omega delta. I end up with omega continuous restricted to this domain. This is this thing. Right? It's exactly because omega delta converges to omega continuous. If I restrict it to this domain, I end up with this. But what I claim is that I can define the second random family of loops by looking at the limit in omega. Okay, I take the limit here, and then I map it by the map f. If you prefer, it will consist in, if you want to stick to the domain f of omega, it will correspond to taking not the square lattice, but the image of the square lattice by the conformal map f, and to take the limit of this. What I claim, what conformal map means, is that it's the same object, that the blue and the red object here is going to be the same. It's a very strong symmetry, because there are many conformal maps in 2 dimensions. In particular, rotation, scale, homothétie, and translations. So it's stronger than the 3 things together. It's a much bigger set of symmetries. And it's such a big set of symmetries that once conformal invariance is proved, you are in heaven as a probabilist. I mean, we are small things, right? We are happy with very little or a lot, I don't know. But if you have conformal invariance, you can prove, you can describe very well everything, because it's such a large class of symmetries that the object itself that are symmetric under all these things are very, very well understood. They are called conformal loop ensembles. They were studied by, in particular, Werner and Sheffield. And you know everything about them. From the point of view of a guy working in the discrete, you know infinitely more than what we know on discrete systems. And in particular, you can prove that the exponent alpha of 1 that I mentioned for the behavior of the porosity, it's equal to 5/36. And I think everybody in their right state of mind will agree that 5/36 is not going to come out of some simple idea. It seems so weird, but it comes once you have conformal invariance. So conformal invariance is the holy grail of our area. And what I want to be telling you now is, how do you get to conformal invariance? How could you get there? So first, let me say that sometimes, in fact, for certain statistical physics systems, conformal invariance is actually known. And this is an absolutely spectacular set of results. So Rick Kenyon, in the end of, the beginning of the 21st century, proved it for dimers. Or maybe in this conference, I should have called it domino tilings, since you had a talk by Alexei Borodin on this subject yesterday. So for domino tiling, conformal invariance is proved. It's also proved for side percolation on the triangular lattice, which is a model related to what I'm discussing, but which is a small variant of it. And it was proved by Stanislas Smirnov in 2001. Smirnov stroked back a second time by proving conformal invariance of the Ising model, and probably the collection of these two results was the reason why he was awarded the Fields Medal in 2010. And it's also known, the conformal invariance is also known for another model, which is discrete GFF, for which it's actually a little bit more natural to expect this. I'm not going to tell you more about that, but I just wanted to mention these things because there are basically a handful of models for which you know conformal invariance. And the reason why you are able to prove conformal invariance there is because these models are, in some sense, miraculously nice in the discrete. They have very nice properties. And these properties, they are not universally shared. Very few models are as nice as those models. So the problem is that we are now stuck. All these results were obtained between 2000 and 2010, but we are facing a big problem, which is that we are not finding other models. There are a few other models, but which are less related to statistical physics and phase transition. So we are not finding new models that are as nice as those models and for which we can prove conformal invariance. And this is very annoying when you attend physics conferences, because they all tell you, but universality, all these models are conformally invariant, you idiots. So, try to do something out of your life. So that's what I'm trying to do. And what we tried is to go back to a more robust strategy that would have a chance to work for more models. Because by working a lot with these models, I really think that these four models that I just stated here are really nicer than the other models. So it's going to be difficult to apply similar techniques to other models. At least that's my bet. So we try to come up with a more robust strategy, a three-step strategy that would be, when you say it, it's a little bit ridiculous, but following basically the conjectures that I mentioned. So first, you prove that the scaling limit exists. So you prove that omega continuous exists. That's the first step. Then you prove that the scaling limit is rotationally invariant. That's the second step, because you remember translation and scaling was obvious, but rotation was not. So you have to prove rotation invariance. And then you try to prove that if you have these three symmetries, scale, translation, and rotation, then automatically you get conformal invariance. And the first time I look at this thing, I thought, for sure, step one is simpler than step two, which is simpler than step three. And I think I got completely wrong. I think step three is simpler than step two, which is simpler than step one. And even that I got wrong, because in fact, the subject of the talk is that we prove step two. So very surprisingly, by trying to actually prove step one, we ended up proving step two. So what is step two? To restate it as a formal theorem, it's saying that the large-scale properties of percolation are invariant of the rotation. That we managed to prove. So what I mean by that is that there is the distance between the random configuration omega delta defined on delta Z2, and the same thing defined on rotation by alpha of delta Z2, the two objects are very close as random objects. For those who know, you can define the distance by saying, by the best coupling, say, and you can prove that this distance is has a very small, is very small between the two configurations. Since I know that not all of you are probabilists and that they could be confused with these statements, let me just give you two consequences of it, and you can forget about the precise statement. So the first thing is that any subsequential limits of the p delta taking delta to 0 is invariant of the rotation. So you don't even need to assume omega continuous exists. You can prove that whatever limit you could obtain by extracting converging subsequences, it will be automatically rotationally invariant. Second thing you can say, and this is maybe the most down-to-earth statement, is that the probabilities that 2 points are connected when the distance between the point goes to infinity, it is becoming rotationally invariant, meaning that it depends only on the L2 norm, the Euclidean norm between the 2 points. And this is very surprising at first sight, because you can really think that because you have the square lattice, maybe another norm is going to be the relevant one, maybe the L infinity one or the L1 norm, the graph distance. Why would it be the Euclidean norm that is going to be relevant? Well, it's the magic of this theorem. It's a Euclidean norm. In fact, you can, the statement above is stronger even than that, but I just wanted, I think this point about probability that 2 points are connected is maybe the most striking one, the first time you see these things. Okay, so in the 5 last minutes, I want to briefly tell you how you prove such a thing. And funnily enough, we are going to prove it by using a universality principle, but like a universality result, but not as big as what physicists want to. We are going to consider a class of models, of percolation models, which is already a good class of model, but not huge. And we are going to prove that the behavior of percolation on this thing is the same. So the class of model is the following. We are going to take percolation model on what we call isoradial graphs. It's a very nice graph structure that I recommend if you like a little bit discrete math, go and read a little bit about isoradial graph. It's beautiful. And it's defined as follows. It's graphs that are embedded in the plane in such a way that every face is enclosed, inscribed, in a circle of radius 1. So this is an example of an isoradial graph. And on this isoradial graph, I claim that there is a natural notion of isoradial weight, which means that there is a natural way to attribute a probability that the edge is open for every edge. It's not going to be the same for every edge, but every edge has a natural parameter P associated to it. I don't want to give you the formula because it's a terrible formula, but I wanted to mention that. 2 examples of isoradial graphs, the square lattice. Obviously, every face is a square, so it's inscribed in a circle of radius 1. Here I drew it in a rotated version just for because it's going to be simpler later. And another one is rectangular lattices, because again, if the rectangle is of the right size, it's inscribed in a circle of radius 1. So this is 2 lattices. I'm going to call it L pi over 2, because here I have an angle of pi over 2, and L alpha, which is because here I have an angle of alpha. Think just of the red guys. The other one is just for ease of the picture. And the theorem that we proved is that, in fact, percolation on this graph and percolation on this one, if you choose the isoradial weights properly, it is very, very close to each other at large scales. Exactly like the rotation invariance thing, but between behavior of percolation on this graph and behavior of percolation on this graph. So how do you do to prove rotation invariance if you have such a universality result? Well, you observe one thing. which is percolation on the graph L pi over 2 is invariant under reflection with respect to the axis, the x-axis, while percolation on the graph L alpha, because L alpha is symmetric under this line here, you end up that the percolation is symmetric under the symmetry sigma alpha, which is a symmetry with respect to e to the I, it's alpha over 2r here, right? There is a typo. So when you have, if the behavior here is close to the behavior here, what you automatically get is that the behavior here is symmetric under the x-axis symmetry, but also with respect to this symmetry. So it's symmetric under the reflection, the composition of the two symmetries, which gives you invariance of the rotation by an angle 2 alpha. Actually alpha, because here it's alpha over 2, sorry. Okay, I'm a little bit late, so maybe I'm going to skip how you prove that the models look the same in both, percolation looks the same in both lattices. It's a beautiful story about the star triangle transformation and connection to integrability. So I'm just going to browse through. You transform, in fact, one lattice into another one using what we call the star triangle transformation. It's a very nice story. But let me directly skip to a more general result, which is that this this Bernoulli percolation result, you can extend it to all FK percolation. So it's much more robust, you see, than what you get just for Bernoulli percolation. And that's something I wanted to mention because it tells you that a priori the strategy seems much more robust. So it's exactly going in the direction we want. So we only prove rotation invariance, but we prove it for a very large class of models, and we prove a form of universality for a large class of models. And in particular, this class of models, it allows to prove rotation invariance of many, many models in statistical physics for people who know, like the Ising model, the Potts model, or the six-vertex model. All those models are rotationally invariant thanks to our result. To conclude, next steps. We did some work, now it's your turn. So first step is to actually truly prove universality amongst isoradial graphs, because what we prove is universality among these rectangular lattices. In fact, our result implies universality for isoradial graph. A PhD student is writing this, so it really gives you some form of universality within a class of models, these isoradial graphs. The question which is harder, but which I think is possible, is to do the, so by the way, this closes the second step of the program to prove conformal invariance. So the next question is to actually close the third step. So prove that if you have scale, translation, and rotation invariance, you get conformal invariance. And this, I must say, I'm pretty confident it's doable. And that already for a physicist would be very good, because a physicist, at least working in this area, will never think that omega continuous is not defined. So for him, omega continuous is defined, and then you need to prove rotation invariance and then conformal invariance. But scale and translation is automatic. So this will be a very good answer for physicists. But for mathematicians like me, what we would also like to do is to prove the first step of the program, which is prove that omega continuous is well defined. And that seems to me already a harder step, hence the two skulls. And an even harder step to have some kind of ranking in the difficulties and work for more years. An even harder step would be to actually prove the universality conjecture. So physicists think rotation invariance is a consequence of universality. I think that this is true, of course, but this is really too big of a conjecture for rotation invariance. You can prove rotation invariance without full universality, and full universality seems to be extremely difficult to prove. But this is a beautiful problem, because it's a problem of whether a mathematical model is actually a good model for physics, because you want universality to be telling you that well, you know, maybe the details of the definition of your models are not that relevant for the behavior of the system. And on these good words, I thank you for your attention, and I'm ready for questions. Thank you very much.
Thank you very much for a very nice and inspiring talk. So we have time for questions.
So there is a small delay, so like that, let me rest.
Yes. Yes.
Oh, I like that.
Okay. So maybe I'll start with a question. So there is this relation of conformal invariant models with an algebraic approach of relating these models with representations of the Virasoro algebra. So is there, and then there are many these finite energy representations of Virasoro, these minimal models and so on. Is there a useful way of getting new lattice models, like you have this representation and you try to construct a lattice or a percolation model that would have this central charge and so on, or that has not been useful in your research?
So in some sense, so it is useful, but in some sense, you see all these algebraic properties of the limits, they are actually ways of understanding conformally invariant objects. So it's kind of exactly the story that starts after you prove conformal invariance. So that's why it's a marvelous world, and it's heaven, because you have all these algebraic structures that enter into the game. Of course, then it makes you, as you mentioned, it suggests that one could try to discretize this thing, or to find discrete analogs of these things to prove conformal invariance, because in some sense, in the limit, you think that you have conformal invariance, so these objects should appear somewhere. It works fairly well when you are, for instance, with the Ising model or dimers or things like that, where you have discrete structures that resemble these continuum ones. Unfortunately, for general models, it doesn't work so well, except that it kind of partially works. So there is this family of integrable systems that actually use these algebraic structures. And these isolated graphs are graphs for which you have integrability. So it gives you not enough, that it's not nice enough that you get everything you want, but in some sense, underlying this whole story, we use integrability of the systems, and this is not that far from this, Young-Baxter, and then you have in the limits from this, you can also get indeed this Virasoro algebra that describes conformal field theory and so on. So all these things are connected, but in order to get some discrete, to build a discrete model that would be very well suited for this Virasoro algebra, this I don't think was ever done. People tried but didn't manage.
Thank you. So I think there are no questions in the platform yet. So maybe I'll make you commented that the one percolation model had very nice relations with algebraic geometry and with number theory. Maybe you could expand a little bit more on that.
Yes, so there was a renewed interest in recent years for percolation models that come from random nodal lines, for instance. So you take eigenfunction of the Laplacian, you sum them at random in some sense. because, I mean, you would like to understand random, I mean, the eigenfunctions themselves, but this is, as everybody knows, a very difficult question. So what you do is you do a mixture of them with random coefficients, and you end up with this type of picture here. I'm sorry I cannot zoom in, but this is the type of pictures you get. And what you can try to see and study is the properties of these objects, the connectivity properties. And they resemble very much Bernoulli percolation. In fact, what is conjecture, it's a beautiful conjecture, is that the large-scale properties of this, I mean, if you want, when delta tends to 0, so you zoom out from this picture, and the connectivity properties, the loops, if you want, the nodal lines, they should converge to omega continuous as well. So maybe that gives you one hint that it's exactly a universality result, and this is one of the most tantalizing conjectures in the field to try to understand that. So this is a connection to nodal lines, but you can also take random homogeneous polynomials, and you are going to end up with a model which is called the Bergman-Fock model. And this one as well should converge to omega continuous in the limits. So these are the connections I had in mind.
And number theory, how does number theory appear?
I mean, the random homogeneous polynomials, it has a connection there. I don't remember exactly. I mean, I don't know so well.
Okay. Thank you very much. Very nice talk. Thank you. So I guess we don't have questions in the platform. So we will have now a lunch break, and we resume at 2 p.m. This afternoon, there will be 2 parallel sessions at 2 and at 4. And don't forget, there is the closing session. It will be at 6 p.m. In this room, so in Pedro Nunes' room. And now, have a nice lunch. Thank you very much, Hugo. Bye-bye. Bye-bye, everyone.
Obrigada, José.